So we've discussed a lot of different ideas about energy, and we've talked about a lot of different types of energy, different ways for energy to be stored. But what we haven't talked about is how time is important, or the importance of time for work being done, for energy being transferred. That's the idea of power. It's kind of crazy to think about it, but all of these climbers, if they started at the same location and they all reached the very peak of this hill, they would all have done the same amount of work. So they all transferred energy really to themselves, okay, by exerting forces and so forth, lifting themselves up to this point. But because when they get to the top, they all have had the same amount of potential energy gained, the same amount of work has been done. And so it's strange, but there's not a difference between these different ways of climbing from a work perspective. The issue is that work has nothing to do with time or really the route that is taken. So if someone's climbing upstairs and they run up the stairs versus someone else who walks up the stairs, if they both start and end at the same point, then they've both done the same amount of work. But certainly running is different than walking. The difference is what we will call power. Power is the rate at which work is done, and it takes into account how much time this requires. So the runner would have a higher power rating than the walker. We can represent that in a formula. Power, capital P, is a ratio between how much work is done during a certain time interval divided by that time interval. This is called the average power, and it's a very important idea because, again, it takes into account the way that the energy is being transferred. So we need to think about, well, how do we calculate that work? There's a number of ways that we might do that. Certainly, we could use the formula that we've talked about before, that force times force applied in the direction of motion or against a direction of motion times the displacement times the cosine of the angle between that. But that's not the only way to calculate work. That force, in a lot of cases, is weight. A lot of times we'll talk about lifting something up. And so if an object is being lifted, the average lifting force would balance the weight. And so the force would be mg, and the displacement would be delta y. Another way of thinking about it is that when something is lifted, it gains potential energy. And so that would equal the amount of work that's been done. A third way to determine the work that's been done is not to calculate it directly, but to think about what work does. Work changes the amount of energy in a system. It transfers energy to or from the object or the system. And so we could look at how much energy it started with and how much energy it ended with. Usually we're talking about kinetic energy there. And we could subtract those two values, taking the final minus the initial. So in summary, make sure you have these things in green written down on your note card. Power, or specifically average power, is the work divided by delta T. Again, lots of ways you can find that work. You can review that on the previous slide if you need to. Power is something that's going to be measured in watts, which a little confusingly has an abbreviation of capital W, which of course is also the symbol for work. So I tend to always use the word watts when I'm labeling my answers. It just helps me not be so confused about it. It's a short enough word here. And a watt is defined as a kilogram meter squared per second cubed. That comes from the fact that a joule, which is what work would be measured in, a joule is a kilogram times meters squared per second squared. You can sort of see that from kinetic energy. And if we take that joule and we divide it by a second, because that's how we'll measure delta T. That's how we get kilogram meters squared per second squared. A useful conversion that comes up in some situations when we're looking at real problems and so forth is the fact that power is often talked about in terms of horsepower for cars, trucks, boats, engines, and so forth. And a horsepower is actually quite a few watts. And so please make sure you have this conversion factor written down. That 1 horsepower, which can be abbreviated HP, is equal to 746 watts.